Welcome to this particular module, and this is a continuation of our last lecture in which we have seen the MOSFET, right. We have seen how the MOSFET can be fabricated using the process flow. Then we have seen how the enhancement MOSFET works. We have seen some transfer characteristics. In this module we will concentrate on depletion type MOSFET, right. So, in the case of enhancement type MOSFET, the channel was not there between source and drain, right. If I say that my index finger and this one is source and this one is drain, then the channel which is this pen was not there, that means channel is not there. So, this channel can be generated when we apply a negative gate voltage compared to the source, or positive gate voltage compared to the source. So, VGS gate is positive compared to source, and then because of the positive voltage at the gate, the electrons will get attracted from the base and there will be formation of channel, right. Due to formation of this channel, as we go on increasing VGS, our current starts increasing, right, for particular value of VDS. For a constant VGS, when we increase VDS, it will reach to a saturation region. When it starts saturating, the constant voltage or VD saturation, it also called the pinch off region, right. And then when we keep on increasing, suddenly it shoots up after on continuously increasing the VDS, and that is your MOSFET may get breakdown, or it is a breakdown region, or the MOSFET may get affected, it may get destroyed. So, we should not exceed VDS more than a particular value. We have also seen that the gate to source voltage should be greater than equal to threshold voltage to see the flow of current, to see the flow of ID, which is drain current, right. So, in this particular module, let us see how the depletion type MOSFET is there, how we can operate it, and what is the construction of depletion type MOSFET. Okay. So, if you see the screen, today we will be discussing about depletion type MOS transistor, its construction and working, as well as its drain and transfer characteristics. Alright, we will see the drain and transfer characteristics, we will see the construction and working of the depletion type MOSFET, okay, not enhancement type, depletion type MOSFET. So, if you see this slide, right, we will see or you can see what is here, this particular figure. If you see, there is a substrate which is SS/B. This is internally connected to the source right over here, right. We are applying VDS where drain is more positive compared to source, and then right now in this particular condition, the gate is directly connected to source, that means that VGS is 0, alright. Now, in this condition you can see source is here, drain is here, and there is already a channel existing between source and drain. There is already a channel existing between source and drain, right. Now, that means that when my VGS is 0 volt, what is my VDS? VDS is nothing but voltage at the drain minus voltage at the source. So, if I increase VDS, my VD will increase and correspondingly my ID will increase. Why? Because I already have this channel present between source and drain. So, in this particular condition, when you have VGS equals to 0, on increasing VDS, we can see increase in drain current, okay. But in case of enhancement type, when VGS equals to 0, even on increasing VDS, we were not able to find any drain current because there was no channel between source and drain. Easy. So, now in case of depletion type MOSFET, what we see that when we apply no gate to source voltage, gate to source voltage is 0. In this case, when we increase VDS, we can see correspondingly increase in current ID. So, what is that? Let us see next one VDS. If I keep on increasing, then the reverse bias will keep on increasing, width of depletion will keep on increasing, and channels becomes narrower and ID becomes constant. ID becomes constant. How? So, if I keep on increasing VDS, right, if I keep on increasing VDS, then my channel will start getting narrowed like this, which you can see from the figure right over here, and because the channel is getting narrow, what will happen? What will happen? The width of depletion region, this width of depletion region is increasing, right. Now, the width of depletion region will be, see, it is like this. So, the width is increasing, the width of depletion region is increasing. Now, if width of depletion region is increasing, that means channel is becoming narrower. If channel becomes narrower, my current ID will be constant, right. And in this particular case, when VGS equals to 0, VGS equals to 0, when my ID, that is my drain current, reaches a constant value, then it is called ID saturation or IDSS. It is called ID saturation or IDSS. However, note that the IDSS is not the maximum current, it is not the maximum current. Okay. We can have higher current if you increase VGS greater than 0, alright. So, that is not that ID constant, ID saturation, that means that we cannot have more than IDSS, it is not a maximum current. We can have more than IDSS if we start increasing VGS greater than 0 volts, right. This was a condition when we have VGS equals to 0 volt. But if I increase VGS greater than 0 volt, I will see the increase in the IDSS or the drain current ID. Easy. Now, if you see the right side of the slide, what you see? If VGS is less than 0, if VGS is less than 0, or let us say VGS is minus 1 volt, VGS is minus 1 volt. Now, what will happen? That means that VGS, that means the gate is negative, right. So, what will happen? The electrons, right, the electrons will be pushed down because electron is negatively charged. We have applied negative to the gate terminal. So, negative will cause repulsion. This repulsion will effect in the pushing the electrons down to the substrate. You can see there is a substrate. So, electrons will come down, it will be pushed down like this, and because a negative charge is there, holes will have positive charge, that we know. So, holes will be pushed up, it will be pulled up, you see, holes will be pulled up, electrons will be pushed down. Okay. So, this will result in recombination of electrons and holes, that is electron in n channel decreases, causes ID to decrease. So, you get it, right. So, if I have this particular condition where my VGS is less than 0, when my VGS is less than 0, what will happen? My electrons from the channel will be pushed down, the holes will be pulled up, and there will be recombination of holes and electrons, and ultimately what I see is decrease in the channel, and the current ID will also simultaneously decreased, the current ID will also decrease. Okay. So, let us consider another condition, that is, in this case my VGS is greater than 0 volt. VGS is greater than 0 volt. So, if my VGS is greater than 0 volt, let us assume it is plus 1 volt. You can see here plus at gate terminal, you have substrate, which is connected to the ground, right, or connected to the ground and also internally connected to the source, that we know. So, here if I have gate which is positive compared to source, then what will happen? The electrons here, right, in the substrate, this will be pulled up. This already n channel is there. You see here n channel, this is electrons within n channel, alright. This forms the channel between source and drain. This is your oxide layer, SiO2, thin layer of gate oxide. We already have seen, right, how can we grow gate oxide? We can grow gate oxide using thermal oxidation, right, thermal oxidation. Now, if I apply positive with respect to the substrate, then what will happen? The electron that are minority carriers from the p substrate will be pulled up, and there will be more number of electrons in the channel. there will be more number of electrons in the channel, that will cause my ID to increase rapidly, that will cause my ID to increase rapidly. Very easy, right? See, we have to just understand positive apply, electron will be attracted, negative apply, electron will be pushed down. If electrons are pushed down, the channel will be narrowed and my ID will be decreasing. If my electrons are pushed up, I can see my ID increasing. Depletion type MOSFET, very easy, right? Very easy. Okay. So, in this case, if I want to draw a drain transfer characteristics, drain and transfer characteristics for depletion type MOSFET, right? How can I draw it? Now, you see here, see this case. Okay. Here you see at VGS equals to 0 volt, I already have on increasing VDS, I will see increase in ID. You see here, let us consider VGS equals to 0 volt, that means we have to consider this line, and you see here there is a current already flowing, right, in case when VGS is 0 volt. So, if I have a VGS less than 0 volt, in this case my current will start decreasing, You can see the saturation IDSS is reaching early, right, and at VGS equals to minus 6 volt, which you can see here is almost gone. But what if I increase VGS greater than 0 volt? If I increase VGS greater than 0 volt, like we discussed, we can see the current still increasing, we can still see the current increasing, the ID is still increasing. That means my IDSS is not the maximum current, right, my IDSS is not maximum current. Because if I increase my VGS greater than 0 volt, I can still see that the current ID is increasing, right. So, what we see here, the drain characteristics is ID versus VDS, right, here ID versus VDS, while the transfer characteristics would be ID versus VGS for fixed VDS. For fixed VDS, let us draw the transfer characteristics. Now, in this case what I will do is I will draw an x and y, xy plot like this. Okay. Okay. And what I will do, I will write down my value for, okay. So, this is 0 volt, this is 1, and then so on in this direction, this is minus 6. What is this? VGS. What is here? Here is ID. Okay. So, what I will write? Minus 6, minus 5, minus 4 until 1, because I have applied the similar voltages, I have applied similar VGS in my this plot, right. So, you see this all the voltages we are writing here in the x axis, right. Now, you see what we have to do, we have to just draw, because this is ID, right. So, we have, and this is also ID, you see this is also ID, this is also ID. So, what we have to do, we have to just connect this ID values like this, right, like this. Like this. Okay. Now, what we have to do? We have to see that what is the value here for current for VDS constant. Let us say VDS is constant. Now, let us consider minus 6. For minus 6 current is 0. So, I will have 0. Minus 5. For minus 5 my current is, let us say 1. So, I will put a star here, then 2, then 3, then let us say current is 4, current becomes higher, still higher, for 0. For 1 I can see here my current is somewhere here, and let us say this value is 8 milliampere. Then what I see is I have points on this axis just by understanding what is the current value for particular VGS value. So, here my plot is ID versus VGS, ID versus VGS. So, again I can draw the transfer characteristics, if I have or if I know the drain characteristics, that is ID versus VDS. If I know ID versus VDS, right, what we are saying, if we know what is how the plot for ID versus VDS looks like for different value of VGS, it is very easy to plot ID versus VGS, correct. What I am saying is, if I know the plot ID versus VDS, how it looks like, it is for different value of VGS, for VGS different values, then it is extremely easy to plot ID versus VGS for same VDS, right, very easy, is not it, extremely easy. So, now if I have a problem, which you can see here, right, the problem is in the conduction region, the rate of current, the current rate of an depletion type MOSFET, the current rate of an depletion type MOSFET is slower than enhancement type MOSFET. What is written? The sentence written is, let us read it together. In the conduction region, the current rate of an depletion or of a depletion type MOSFET is slower than the current rate in enhancement type MOSFET. Is this statement true or false? That is a question, right. So, let us, we have to find out whether this statement is true or false. The statement is, if I use my MOSFET, right, one is my depletion MOSFET, one is my enhancement MOSFET, and what it says that in conduction region triode in conduction region my rate of change of current, right, that is my ID, that is my rate of change. So, dID by dVGS, right, rate of change of current is slower when I use depletion compared to when I use enhancement. Is it true or is it false? So, let us solve it. Now, we all know that the ID formula for depletion type MOSFET is nothing but ID equals to IDSS 1 minus VGS by VP whole square, correct. And if I want to understand enhancement type MOSFET, then my current formula ID will be ID equals to K times VGS minus VT whole square. We will see derivation of one of this, right. Rest you have to do by yourself, try to do by yourself as well. So, once I know the formula ID equals to IDSS 1 minus VGS by VP whole square and ID equals to K times VGS minus VP whole square, then what is the constant here? Here my constant is IDSS and VP, here my constant is K and VD, right, because here IDSS is constant, we know it, here pinch off voltage is constant, I know it, here K is constant, I know it, here threshold voltage is constant, I know it, correct. So, in this case, if I do the derivation, because I want to see the rate of change, that is why I have to do derivation. So, dID, this particular equation 1, here is also equation, let us say make it 2, let us say this equation number 2. So, we are deriving from 1, okay. So, 1, if you see further, dID by dVGS, right, equals to IDSS IDSS is constant, d by dVGS of 1 minus VGS by Vp whole square, right. So, let us just see this side first, okay, this side first, left side, this side first. So, let us assume here that 1 minus VGS minus divided by Vp, 1 minus VGS by Vp is nothing but my constant S. In that case, did by dVGS equals to 2 times IDSS d by dVGS of S, correct, because d by dVGS of 2S of S square right, because we have considered this value 1 minus VGS by Vp equals to S. So, we can have dVGS d by dVGS of S square, that can be nothing but 2 times d by dVGS of S, right. That was we are written, see, 2 times d by dVGS of S, right, and 2 times S 2S d by dVGS of S, right. So, 2 times S d by dVGS of S, and then we have your IDSS, right. 2 times, when you have this derivation of S square, it is 2 times S d by dVGS of S, right. So, that is only a simple derivation by which we can get this formula, which is right in front of you, is nothing but dID by dVGS is nothing but 2 times IDSS into S into d by dVGS into S, right. So, with this formula, if I substitute the value of S, my S is nothing but 1 minus VGS by Vp. So, if I substitute value of 1 minus value of S in here 1 minus VGS by Vp, then I get this particular formula. So, if I further understand 2 ID 1 minus VGS by Vp, now derivation of 1 is 0, right, and d by dVGS of VGS by Vp will be minus 1 by Vp. So, if I further solve this equation, what I have, d by dID by dVGS, dID by dVGS is 2 times IDSS. Now, you multiply this and this, what you get, Vp square VGS minus Vp, Now, what is constant here? We know, see, IDSS is constant and Vp is constant, we know, right. So, let us put the constant value. So, this means that this particular value is constant, right. 2 is constant, IDS by Vp whole square will be constant, VGS minus Vp is again constant. So, I will write C as a constant, VGS minus C, which is again a constant. So, my role or my equation for the depletion region, for the depletion MOSFET is C VGS minus C. This is my equation for what? Depletion time MOSFET, and that too in conduction region, the rate of change of current. Now, I had to see how the rate of change of current or the current change occurs in the enhancement time MOSFET. I will see how the change of current occurs in enhancement time MOSFET. So, let us consider the right side of the slide, and second half, that is the equation number 2. So, now we will just consider this particular side, alright. So, let us start. So, now we know that enhancement time MOSFET, your current ID is K times VGS minus Vt whole square. Here K is constant and Vt is constant, right. K is constant, Vt is constant. So, if I start derivating, my dID by dVGS means nothing but K times d by dVGS of VGS minus Vt whole square, right. Now, if I assume VGS minus Vt is equal to M, then I will have dID by dVGS equals to 2 times Km dm by VGS. Again, it is similar thing, right. What we have is d by dVGS of M square. This is nothing but 2 times M d by dVGS of M, right. This is what we have written here. K is there, so we have substituted K also. Alright. Now, once I have this, right, I will again substitute value of M. So, when I substitute value of m, I will have 2k, m is what, VGS minus VT. So, 2k into VGS minus VT d by dVGS of VGS minus VT. When I solve this, I will get 2k VGS minus VT, 2k VGS minus VT. Now, d by VGS of VGS minus VT is nothing but, see, VGS, so 1 and VT is constant. So, my 1 minus 0 is 0. So, here my value is nothing but, this is constant, right, this is constant and VT is constant, right. So, it will be constant into, it is writing like constant because k is constant, right, 2 is constant, VGS minus VT, VT is constant. So, I have value d by dID by dVGS equals to C times VGS minus C. This is what I have derived. This is what I have derived. This is for enhancement type, right, enhancement type. This is for depletion type MOSFET. So, what I find is that in the conduction region, the current rate of an depletion type MOSFET is equal to the enhancement type MOSFET, right. In the conduction region, the current rate of an depletion type MOSFET is not slower, not faster, but it is equal to the current rate of change in enhancement type MOSFET. So, this statement is false. So, this statement is false. Easy, super easy, right. This is how we can derive, whether the rate of change of current in depletion type MOSFET is different than rate of change of current in enhancement type MOSFET. Okay? All right. So, if I see the characteristics, it is just to help you out once again. You see, VD saturation is VGS minus VT. We just understand this plot. Okay, ID, you can see almost a straight line, and then the curve bends as the channel resistance increases with VDS. This is your nothing but VDS saturation, which is here. This region is your triode region. Once it saturates, current saturates because the channel is pinched off. So, this is a pinched off voltage, and here in saturation region VDS is greater than VGS minus VT, right. So, if I see this particular plot, what I see, there is a source, there is a channel, there is a drain, here there is a drain, here there is a source, right, and there is a formation of charge. The velocity is nothing but dx by dt. This is my x, right, my x, velocity is dx by dt. My E will be nothing but dvx by dx, right, where this is my voltage Vx, this one, and this will be my dvx, right. You see here, this one will be my dvx, right. So, if I want to draw voltage plot and to see how the channel is formed, right, I can find the velocity, I can see the charge, I can see what is the electric field, and that is how we can derive the ID versus VDS characteristics of a MOSFET. You can again see the symbol of enhancement type MOSFET, you can see that depletion type N channel MOSFET, generic N channel MOSFET, but you see enhancement type, there is a break between the drain and source, and the reason is that there is no channel at the starting of the MOSFET, right. When you take a MOSFET enhancement type, there is no channel, but in case of depletion type, there is a formation of channel and at the starting, and that is why we can see this particular line, right. Easy, very easy, right, very easy. So, let us do one more example and then we will finish this particular module, right, and we will continue the next module of the same lecture, all right. So, if you are given determine Vt, that is threshold voltage, for k of some value, ID on for some value, with VGS on for some value, right. So, first is we should understand that VGS on is 4 volts ID on is 3.5 milliampere. That means this is nothing but my enhancement type MOSFET. For enhancement type MOSFET, for triode region I know the equation, for triode region ID equals to 2 times K into bracket VGS minus VT into VDS minus VDS square by 2 bracket over. This is my equation for triode region. For saturation region I know VDS equals to VGS minus VT, right. So, I will substitute this value, right, substitute this value of VDS into this particular equation. What will I have? Substituting 2 in 1, I will have ID equals to K times VGS minus VT whole square, correct. Now, I already have ID. What is ID? 3.5 milliampere, right, it is already given here. I have VGS 4 volts, right. VT I have to find it out, right. K is also given 0.4 into 10 to the power minus 3 ampere per volt square. This everything is given, right. So, if I substitute the value, what I find is, if I substitute value 3.5 equals to this value, then I will have here this particular equation, right. So, this particular value I will put it here and I will solve it. So, I will have 8.75 volt square equals to nothing but 4 V minus VT whole square. Now, this gone. So, 2.95 equals to 4 minus VT, right. So, we can have by taking square root, right, by taking a square root of this particular equation. If I take square root of this particular equation, then what will happen? I have 2.95 volts equals to 4 V minus VT, then I have VT equals to 1.05 volts. Easy, very easy, right. So, if I know what kind of MOSFET I have, I can find out VT, because I know that in saturation region VDS equals to VGS minus VT, triode region this is the equation. I substitute this equation, I will have an equation for drain current. In the equation of drain current everything is given, ID is given, K is given, VGS is given. I have to just find out threshold voltage VT, right. So, this is the last slide for this particular module, and we will continue in the next module and see the further application of the MOSFET. Okay. So, I hope that you guys understood what is a depletion MOSFET. You understood quickly what are the drain characteristics. We have seen an example of whether the change in the rate of change of current in the conduction region in depletion type and enhancement type is same or different. We found that both is same. Then we have seen an example of determining the threshold voltage. All right. So, in the next slides, in the next modules, what we will be looking at? We will looking at the derivation of MOSFET current to voltage characteristics. All right, derivation of MOSFET current to voltage characteristics. We will quickly see what is channel length modulation, and then we will move to the important application of this MOSFET, which is your current mirror. Okay. So, till then you just go through the lecture, right. Read it once again, how the depletion MOSFET can be used compared to enhancement type MOSFET. The application is very simple. In enhancement type there is no channel, in depletion type there is a channel. When there is no channel, if I want to attract electron, I have to apply positive gate. That is why gate is positive. That means when I increase VGS, my current will start increasing. In this case, but there is already channel. So, even at VGS equals to 0, that is in depletion type, there is a channel between source and drain. So, VGS equals to 0, still I see some current ID, and if I decrease this VGS, then I will see a decrease in the current ID. But if I increase the VGS, then it can be more than IDSS, because IDSS is not the maximum current. All right. So, this much things we have understood till now. Now, let us see what we can learn in the next class. So, I will see you in the next class. Till then, you take care. Bye.